Okay, good morning. Let's get started. Sorry for the delay. So, as usual, please scan this one. This we need to check. Okay, good morning again. So, the part on material science is pending, but it need not be sequential. I will teach that portion some other time. Let's get started with magnetism today. So far I notice 29 of you have joined the book club. First question, like how did you come across magnets at first? Okay, so many of you have said the fridge magnets, toys, broken speaker, inside the speaker, loudspeaker, all those things. So basically you get fascinated with the magnets because when you see magnets they attract something and they repel each other, and this is the property that as a child basically attracts people towards magnets. Okay. So, this property of attraction or repulsion comes from the fact that magnets produce a magnetic field. Okay. So, as you know, field is something that can produce force without contact. So, if you hit a tennis ball with a racket, there is a contact force, because of that contact force the ball moves. Okay. On the other hand, you keep a charge in the electric field, the charge will be attracted even without a contact. If you have magnet and if you keep a magnet, I mean iron, piece of iron next to a magnet, magnet can still attract, there is a force without contact, and that is what we call as field. So, magnets generate magnetic field, and this magnetic field can be used for many different purposes. Okay. For example, as many of you have written, fridge magnets is used to attract the magnetic material, and magnets can produce a force. So, you know that in motor we have magnets and we use a combination of electric current and the magnetic field to produce rotational motion, and the magnets can also be used for levitation. There are maglev trains. So, in China they have trains that go from Shanghai airport to the city at speeds of 400 kilometer per hour, okay, without friction, because it is a levitated train. So, this is also possible because of a magnetic field, and you also know that we can generate electricity from time varying magnetic field. So, if you look at the old bicycles, there will be a dynamo. So, there will be something that will be touching the tire. So, when the tire rotates, the dynamo rotates. Dynamo basically has a magnet and the magnet rotates. So, when there is a time varying magnetic flux as a function of when there is a time varying magnetic flux in the presence of a coil, you can generate electricity, and this is the principle we use in dynamos and transformers. And we can magnetize magnets in one direction or the other. So, you can keep the north pole up, south pole down, or south pole up, north pole down. You can magnetize material in different direction, and you can use this magnetic field to sense information, and this is what is carried out in magnetic recording. And you can also sense the magnetic field to know the bits. So, in magnetic recording, magnets generate magnetic field, and we sense that magnetic field to read the information, and we use compass for navigation and so on. Okay. So, with magnetic field we can do so many things. So, that is one reason why magnets are interesting. Okay. Okay, that brings us to the next question. So, I talked about navigation. So, there is a question about navigation in your book lab. It's okay. It's okay. Okay, quite often, I mean, when I teach a class full of Chinese, they will choose Chinese. Okay. I don't know why you guys chose the Europeans, because Chinese is the first people to invent compass. Okay. The compass based on magnets was invented by Chinese. So, that is what many people will choose, and still all of you are wrong, all of you are wrong. The correct answer is others. Okay. So, my question is who? Okay. It does not mean only human. The first living beings used magnetic field for sensing, or actually bacteria and birds. So, you know that bacteria and birds evolved earlier than humans, and they have been using magnetic fields for navigation. So, Chinese invented only like 1000 years ago, but even before that bacteria and birds used magnetic field for navigation. Okay. So, now we have learnt about magnetic fields, how it can be used in various ways. So, now let us take a few steps to learn how we can generate a magnetic field. Okay. So, you know that you can generate a magnetic field by using a permanent magnet. Okay. So, if you have a magnet, you bring it near the fridge, it will stick, because that permanent magnet is generating a magnetic field. It's in the pen mode. Okay, so permanent magnet is one way to generate a magnetic field. Then you can also generate a magnetic field by using current carrying wires, solenoids or electromagnets. Okay. So, for example, you take a piece of wire, you apply an electric field, electrons flow, and as a result you will see that there is a magnetic field generated. So, magnetic field is produced when there is a motion of charges. So, electrons flow in a wire, produce a magnetic field. Okay, again another question, do you have any idea like when possibly this kind of phenomenon happen in the world? So, you know, one example is the Oersted, the scientist, he sent current through the Ampere, I do not know who it is. So, he sent current through the wire, then he observed that magnetic field is produced, but is that the first occurrence of such magnetic field produced by current carrying wire? No. Okay. For example, you take brain. So, in our brain we have neurons. So, neurons are connected to each other through something called axon. So, when we do any computation or something, there is a electrical current flowing from one neuron to the other neuron through axons. Okay. So, that current also produces a magnetic field. So, our brain, when our brain operates, it produces certain magnetic field, and we can use this magnetic field to sense to understand the brain's working function. So, if you have heard about magnetic encephalography. So, in magnetic encephalography, we are sensing the magnetic field produced by the current flowing from one neuron to the other neuron. So, that produces tiny magnetic field, like very low magnetic field, 10 power minus 15 Tesla, that kind of very low magnetic field is produced by our brain. So, these are examples of flowing charges producing a magnetic field. Okay. So, in this case you can use your finger to know the direction. So, if the current is flowing in the direction of your thumb, the magnetic field is in the direction pointed by your fingers. Okay. So, this is the Biot-Savart law. So, the field produced at any particular radius is given by this formula. So, it is proportional to the current and it is inversely proportional to the radius at which you measure the current. So, as I have told you, this is happening in real life in your brain. Even when you are learning the magnetism, your brain is firing and there is flow flow of current from one neuron to the other neuron, you are producing magnetic field as you are listening to this conversation, and that is one application. The second application is that this principle was used in one of the earlier forms of magnetic random access memory. So, we used this magnetic field to write information in MRAM. So, that was one another application.
I'm going to sprinkle some iron filings onto the plastic. I will now apply a current, and I will have to tap the plastic to get the iron filings to move. And you can see how the iron filings have rotated to form circles around the wire, indicating the form of the magnetic field intensity generated by a current carrying wire.
Okay, if the current is flowing in this direction, the iron filings will follow the fingers. Okay. So, that is one way of producing a magnetic field, and we don't use that much in our labs. Okay. The second method to produce magnetic field is by creating solenoid and sending a current through the solenoid. You can produce magnetic field. So, I do not know, many of you would have come across Helmholtz coil in your laboratories. So, in Helmholtz coil you have a lot of wires wound in certain fashion. So, by sending a current through the Helmholtz coil, you can produce a magnetic field. So, there the field is given by this formula N I over L, where N is the number of turns and L is the length. So, we can also say N is the number of turns per unit length, and I is the current that you sent through the Helmholtz coil. Okay, so, sometimes you may wonder which side is north or south. So, you can use this mnemonics to understand which is the north pole or south pole of a Helmholtz coil. Let us say you look from one direction and the current is flowing in this fashion. Okay, so, this looks like north, right. So, this is the north pole. In the other direction the current will flow in the other way. So, this is the south pole. Okay. So, this is a mnemonics you can use to understand which one is the north or south pole. The third way, which is the most common way to produce a magnetic field, is to use an electromagnet with a ferromagnetic core. Okay. So, electromagnet with a ferromagnetic core is very similar to the solenoid that we saw in the previous slide, except that in this case we introduce a magnetic material into the core of the solenoid. So, this magnetic material has a property called permeability. So, this permeability can be 100 or 1000 depending on the material that you use. So, this permeability will multiply the magnetic field produced by a normal coil. Okay. Normal solenoid only produce a magnetic field of N I over L. Okay. Whereas, when you introduce a magnetic material with a permeability mu r, the magnetic field is amplified by this factor. Okay. So, if you produce like 1 Tesla, 1 worsted with a coil, and if you introduce a magnetic material with a permeability of 1000 for example, the magnetic field will be amplified to 1000 worsted. Okay. So, this is the use of the ferromagnetic core. So, if you look at this picture, so we have 2 cylinders, right, there are 2 cylinders here. So, here we have coil. So, there are lot of wires wound here, and in between you can see a gray color cylinder. So, this gray color cylinder is the electromagnetic material, the ferromagnetic material. It amplifies the magnetic field by this factor, which is permeability. So, here the field strength depends on the current that we send, the number of coils per length, and it also depends on the permeability. Okay. So, normally this cylinder you see can be of two different shapes. Okay. So, it can have like flat edge on one side and another side it may have a cone like structure. Okay. So, when you have this one you can switch the directions of the the core, ferromagnetic core. So, this red color thing what you see here is the ferromagnetic core. So, by switching, so you can make the two cones face each other or you can make the two cylindrical parts face each other. So, you can achieve two different configuration. Okay. So, in this configuration the magnetic field shown by these lines are over a narrow range, but the magnetic field lines are dense, you can see. Okay. That means, we can produce a strong magnetic field, but this field is uniform over a small area. Okay. So, that is one configuration. In the second configuration, we can produce a weaker field. You can see the number of flux line in the same area is lower. Okay. So, we produce weaker field, but this field is uniform over a large area. So, depending on what you want, whether you want uniform field or whether you want strong field, you can choose any of these configuration. Okay. So, these electromagnets are very common. So, you go to any lab where they work on magnetism, many of these labs will have electromagnet with a ferromagnetic core. Okay. So, these are some of the ferromagnet that we have in our lab in Singapore. So, this basically this slide tells you why we need a ferromagnetic core. So, if you just use a Helmholtz coil, you cannot produce a very strong magnetic field. On the other hand, when you introduce a material like iron or mu metal with a high permeability, the magnetic field gets enhanced by the factor mu r. Okay. So, that is the reason. Okay, let us do this question now. So, when this question comes, maybe they can focus the camera to this. Okay, I will stop after I get 35 answers. Now, 33. 34, 'Okay. Okay, all of the above happens is the correct answer. So, when you send a current through a wire, you produce heat because of the Joule heating. You produce a magnetic field, that is what I taught you, and of course, there will be a potential difference between the two ends. So, all of the above happens. Next question. Okay, I will stop now. Okay, all of you are right, very good. Next question. Okay, majority of you are right. The correct answer is you can enhance the magnetic field more efficiently by inserting a magnetic material with a relative permeability. Okay. So, I told you that the magnetic field purely due to current is N I over L. Okay. So, if you want to enhance the magnetic field by 100 times, you have to increase the current by 100, a factor of 100, okay, which is not efficient way. On the other hand, you just insert a magnetic material with a permeability of 100, then you can enhance the magnetic field. So, the efficient way is to insert a magnetic material with a high relative permeability. Okay, so, now let us move on to the next discussion. So, we learned that we can produce magnetic field by flow of charges. So, the charges can flow in a straight line or it can flow in a curved path. Okay. So, it can generate magnetic field, but we also have learned that we can produce magnetic field with a permanent magnet. So, if you bring a permanent magnet near a fridge, the permanent magnet will stick to the fridge because the permanent magnet is producing a magnetic field. So, here we are not sending any current. So, why does the permanent magnet produce a magnetic field? So, this is the question that we will be discussing in the next few minutes, even until tomorrow. Okay. So, in solenoid you send a current and it produces magnetic field, and in the bar magnet also you can see a magnetic field. So, the north pole, south pole, they all look identical. Okay. So, even when we are not sending any current through the permanent magnet, we are still able to produce magnetic field. The reason is one case is classical electrodynamics. So, when you talk about sending current to produce a magnetic field, that comes under classical electrodynamics. But for understanding how a permanent magnet works, we need to understand some aspect of quantum mechanics. Okay. So, in this course I will not go too much into the quantum mechanics, because you would have all studied quantum mechanics before, but I will touch upon the basics. And also in this course I am not going to teach everything about magnetism, but what is needed for understanding the MRAM, okay, magnetic random access memory. Sometimes you all learn lot of aspects of magnetism. Quite often some simple facts are missed. Okay. So, I am going to teach the simple facts that are necessary for understanding the functioning of a magnetic recording or MRAM. So, the treatment of magnetism will be a bit different here. Okay. So, to understand the magnetism that comes with a permanent magnet or magnetic material, we need to understand some of the properties associated with electron, such as orbital magnetic moment or spin magnetic moment. So, these terms we will be using very often. So, in future I mean for the next few days. I mean we are going to be together for another 8 days. So, in all those days if I use the term magnetic moment, basically I am referring to a tiny magnetic dipole. Okay. So, you know that magnets have 2 poles. So, this is what we call magnetic dipole, right. So, moving forward for the next few days, when I say magnetic moment, I am talking about a tiny magnet which may look like this. So, but we do not draw like rectangle, draw north south pole, but simply we use symbol arrow. Okay. So, arrow like this represent a tiny magnet with a north pole. So, the arrow head is basically the north pole and this tail is the south pole. Okay. So, we use this symbol arrow to represent magnetic moment. So, I will be drawing lots of arrows in the next few days. Okay. So, whenever I draw arrow, you remember that it is a tiny magnetic dipole. Okay. And the discussion from here on, I mean although I start this slide with the permanent magnet as the title, but whatever discussion we are going to do in the next few hours is not just related to permanent magnet, but it can be applied to many magnetic materials in general. Okay. Okay, let us do another question before we move on. Okay, all of you are right, very good. Next question. Next question you can answer anything other than ferromagnet. Okay. Okay. So, the key word here is attractor. Okay. So, you have chosen iron to be a magnetic material because you saw that iron got attracted to a magnet. Okay. So, that brings us to the next slide. So, I asked you to avoid the term ferromagnet because I want you to think like a common person, okay, not like a physicist who have studied some aspect of magnetism. Okay. So, if you ask a normal person who has not studied physics to describe materials into two types, then they will have only two types, right. One is a magnetic material, another one is a non-magnetic. Okay. So, how do they divide this? They divide this based on whether a material get attracted to magnet or it does not get attracted to magnet. Okay. So, when material gets attracted to magnet, they call it magnetic, and if the material does not get attracted to a magnet, they call it non-magnetic. So, this is the non-physics way of classifying materials on magnetism, but physicists have classified magnetic materials into 5 different types. Now, there is a 6th type which we can discuss if there is time, but traditionally there are 5 types of magnetism according to physics. Okay. So, the ferromagnetic and ferrimagnetic materials, they get attracted to magnet. Okay. So, that is what a common person calls magnetic, whereas there are some other materials which do not respond to magnet in a significant way, but they still respond to magnets in certain way. Okay. I will show you some videos to explain some of this aspect, and based on their property, they physicists have given the names paramagnetic, diamagnetic and antiferromagnetic. Okay. So, for the next few hours we will be learning what differentiates these different materials and so on. Have anyone seen ferrimagnetic material? Okay, you have seen. Anyone else? Only one. Which one have you seen? YIG. Okay. YIG you have seen. Anything else? Pardon? Fe3O4 you have seen. Okay. Anyone else? Have anyone seen the old speakers with the black magnet? Have you seen? Or even the fridge magnet, the black fridge magnet, right? So, that is some kind of iron oxide, that is a ferrimagnet. Okay. So, you all know ferrimagnet, but you do not know that it is ferrimagnet. Okay. So, the black magnets are called ferrite. So, ferrites are ferrimagnets. So, we know that cobalt, iron, boron, they are all ferromagnet, and we have also seen lot of ferrimagnets, they also get attracted, and fridge magnets are ferrimagnets. Okay. So, you can see that it gets attracted to the fridge. So, this is what common people call as magnet, but these are also magnetic, they respond to magnetic field in certain different way. Okay. So, from a lay person's perspective, only ferromagnetic materials are magnetic, ferrimagnetic materials also get attracted, and scientifically all materials respond to magnet, respond to a magnetic field in different ways. Okay. So, these are examples of paramagnetic materials, diamagnetic materials, antiferromagnetic materials and so on. So, ferro and ferrimagnetic materials, they will be attracted to magnets. Paramagnetic materials will be weakly attracted to magnets. So, this weak is like very difficult to see. If you have a very strong magnet and you bring a piece of aluminum, then you will notice that the aluminum gets slightly attracted. Okay. But this attraction is very weak. At diamagnets get repelled by magnet, this again weak. Okay. So, people use some magnetometers to measure whether or to find out whether material is paramagnetic, diamagnetic and so on, which we will learn later. But I want to show you this example that diamagnetic materials get repelled by magnet. Okay. If you take a frog, for example, frog has very few bones, very light bones, and the body of a frog is made up of around 80% water. Okay. Water is diamagnetic. Okay. So, in this experiment what the researchers did is they got a 7 Tesla magnet to play with. So, it is on a Friday afternoon. So, this group basically Friday afternoon they have fun. Okay. So, what they decided to do, they put the frog on top of a 7 Tesla superconducting magnet. Okay, then they saw that the frog was floating. Okay. Because the frog has like 80% water, water is diamagnetic, and there is a magnetic field coming from the bottom of the magnet. Let us say this is the magnetic field is coming this way. They put the frog and the magnetic field repels the frog, magnetic field repels the frog. So, the frog floats. Okay. And that is what they see. So, usually when I see this video, some people ask why didn't the frog jump off, why was it floating? Yes. Why wasn't the frog jumping off? Why was it floating? Pardon? Yeah, it needs to kick into something to jump, right? It was not able to kick. There is nothing to produce a force. It cannot produce a force. Okay, so this is one example that the diamagnetic materials are repelled by magnet. So, that was a 7 Tesla magnet. Okay. Can we show the repulsion between?
What I'm going to show you today is how everything is magnetic. So we all know that yes, a magnet can attract another magnet, but what you might not have known is that everything is magnetic. Water, air, people, wood. So I'll show you. Repel the magnet and get pushed.
Kind of looks like you're touching it.
Not touching it.
Prove it. Oh, there you go.
Push it back. Not touching it. Not touching it. So water repels a magnet.
Okay, so you don't need 7 Tesla magnet to show that magnets repel diamagnetic material. Even when you use smart structures like this, you can see the repulsion between magnet and water, which is diamagnetic. Okay. So, let us do one question. Okay, most of you are right. Okay, there are a few wrong answers, but mostly all of you are right. So, ferromagnetic materials are strongly attracted to magnets, ferrimagnetic materials are also strongly attracted, paramagnetic materials are weakly attracted, and diamagnetic materials are weakly repelled. Okay, so moving forward, you will learn many new terms. If you haven't learned magnetism before, you will learn many new terms, okay, and we will be learning about various types of magnetic materials, what their properties are, how they respond to magnetic field, and so on. Okay, I briefly showed what is a magnetic dipole before. Basically, you have a magnet with two poles. So, this is what we call magnetic dipole, and if you haven't learned before, you would have seen electrical dipole before. So, it is very similar. So, magnetic dipoles generate magnetic field. So, where does that magnetic dipole come from? So, for that we need to understand the terms like orbital magnetic moment, spin magnetic moment, and so on. Okay. So, as I showed you, as I told you before, whenever I draw an arrow is a symbol for magnetic moment. You can imagine like a tiny magnet with a north pole here, south pole here, something like that. Okay, so first let us discuss orbital magnetic moment. So, you know that in atoms, electrons go around the nucleus. So, you know that charges in motion produce magnetic field. This is what we learned a few minutes ago. We learned that when charges flow, they produce a magnetic field. So, in this case, the motion of electrons around the nucleus produces this orbital magnetic moment. Okay. So, the unit for magnetic moments is a Bohr magneton. So, when electrons flow around the orbital, then the electrons have certain Bohr magneton. Okay. So, one Bohr magneton has this value. So, 9.27 10 power minus 24 ampere square meter. Okay. So, this is difficult to understand. So, you can imagine a 10 microampere current flowing through a wire with dimensions 1 nanometer, 1 nanometer. Okay. Imagine such a current flows through a loop of 1 nanometer square dimension, that will produce certain magnetic field, and that is equivalent to 1 Bohr magneton. And okay, so the flow of electrons around the nucleus produces orbital magnetic moment. Okay, and this is probably the last slide. I am going to talk about orbital magnetic moment, because in most common magnetic materials that we use like iron, cobalt, nickel, in all these magnetic materials, the orbital magnetic moment is said to be quenched. Okay. So, this quenched is a quantum mechanical term. So, you can derive some equations, and finally, you will find that this orbital magnetic moment becomes 0. Okay. So, the quenched is the technical term to say that the orbital magnetic moment contribution is 0. Okay. So, that in simple words, quenched means 0. Okay. So, the orbital magnetic moment does not play a big role, but for the completeness I just briefly talked about it. So, what contributes to the magnetic properties of materials like iron, cobalt, nickel is mainly coming from the spin of electrons. So, yesterday we discussed various definitions of spin, but if you do not understand, just accept that electrons have spin, and the electron spin is like having certain magnetic property. Okay. So, you can say that certain electrons have north pole up, south pole down, certain electrons have north pole down, south pole up, something like that. Okay. So, this spin magnetic moment is the main contributor to the magnetic properties that we see in materials like iron, cobalt, nickel. Okay. So, we know that the electrons are filled in certain order. Okay. So, to understand the magnetic property of iron, let us take iron nucleus here. Okay. So, this is iron nucleus, and we are going to look at how the electrons are filled in different shells of iron orbits. Okay. So, we know that according to Pauli's exclusion principle, no two electrons cannot occupy the same quantum state, and we also fill the electrons according to Hund's rule. Okay. So, firstly the 1s shell will be filled with 2 electrons. So, one spin up, one spin down. Then we have 2s shell again filled with 2 electrons. 2p will have 6 electrons. So, 3 up, 3 down. Okay. After 2p we have 3s, again one spin up, one spin down. Then after 3s we have 3p. So, 3 spin up, 3 spin down. So, after 3p, 4s will be filled. Okay. So, 4s will have one spin up, one spin down. So, iron has 26 electrons. So, we have filled 20 electrons. Okay. So, we are left with 6 electrons which will go into the 3D. So, 3D can accommodate 10 electrons. So, first it will be filled with 5 electrons up, and we will have 1 electron which is spin down. Okay. So, in all the other shells except 3D we have compensated spin. So, let us say this contributes to certain Bohr magneton. So, that value is cancelled by the spin of the opposite type. So, there is no net magnetic moment in any of the other shells except 3D. Okay. So, each electron has a magnetic moment of 1 Bohr magneton. Okay. So, here all it will become 0 0 0, but here you see there are 5 spin up electrons and 1 spin down electron. So, we will have 5 minus 1 Bohr magneton. Okay. So, we can simply say that if you take one iron atom, isolated iron atom will have a magnetic moment of 4 Bohr magneton. So, we can consider this as a unit for magnetic moment. Okay. So, this is one kind of unit for magnetic moment. For distance we use meter, kilometer, mile. So, in a similar sense you can take this mu b as the unit for magnetic moment. So, if you take one isolated atom of iron, so it will have 4 Bohr magneton. So, this is the magnetic moment of one isolated iron atom. So, now let us look at the materials that we know. Iron is a ferromagnet. Iron has 26 electrons. So, 5 up, 1 spin down, 5 spin up. So, we have 4 unpaired electrons. So, we can say that iron has 4 Bohr magneton. Cobalt will have 3 unpaired electrons. So, if you take isolated cobalt atom, it will have 3 Bohr magneton. So, nickel has 2 unpaired electrons in the d shell. So, we can say nickel has 2 Bohr magneton. So, in some sense we can roughly infer that if you bring a piece of iron next to magnet, iron will be strongly attracted than cobalt and then nickel. Okay. We can roughly infer this behavior just from the simple perspective of how the electrons are arranged in the d shell. Okay. But it gets a bit tricky. You take chromium for example. Chromium also has 5 unpaired electrons. So, chromium atom also should have 5 Bohr magneton. Manganese also has 5 unpaired electrons, it should have 5 bohr magneton. But if you bring a piece of chromium next to a permanent magnet, you will see chromium does not get attracted, manganese does not get attracted to magnet. So, what happens? There is something else missing here. Okay. So, only some elements with a certain magnetic moment, they are magnetic, but some elements with a certain magnetic moment are not magnetic. Okay. So, something else we need to take into picture. Okay, let us say we put many atoms of say any of these elements together, there are many possibilities. So, one possibility is that you put many atoms with magnetic moments next to each other, they all lie parallel to each other, this is one possibility. Okay, the second possibility is that you put these magnetic moments next to each other, they align anti-parallelly. This is another possibility. Third possibility is that you bring many atoms with magnetic moments next to each other, they do not have any preference, they are randomly aligned in any direction. Okay. So, all these three possibilities exist. Okay. And these possibilities are the one that determines whether a material is ferromagnetic or antiferromagnetic or paramagnetic. Okay. So, there is some phenomena that makes the neighboring magnetic moments to be parallel or neighboring magnetic moments to be anti-parallel, or it does not do anything. Okay. Neighboring magnetic moments are just random. Okay. So, what is that property that brings this phenomena was not known until say 100 years ago. So, before 100 years ago, people did not know what makes the neighboring magnetic moments parallel or anti-parallel and things like that. So, people had various explanation. So, one of the explanation was given by Weiss. This theory is outdated. So, he thought that there is some internal magnetic field inside material, and that magnetic field is the one that aligns the neighboring magnetic moments parallel to each other. Okay. So, Weiss thought that there is some internal magnetic field inside material, and that is what makes the neighboring magnetic moments parallel to each other. Okay. So, that was the concept, but if you do analyze, this field will be very strong. Okay. The field that you require to force the neighboring spins of say 2 iron atoms parallel to each other will be like 1000 Tesla, which is like 100 million times stronger than the Earth's magnetic field. Okay. So, this theory is now outdated. So, around 100 years ago, Heisenberg came up with the quantum mechanical description of what makes the 2 neighboring spins to be parallel to each other. Okay. So, we will not go into the quantum mechanical derivation of everything, but we just come to the result. Okay. So, Heisenberg states that let us say we have 2 spins S1 and S2. These are vectors. So, the energy between these 2 spins will be given by this formula. Okay. So, this J is called the exchange integral. So, this comes from quantum mechanical derivation. So, the energy between 2 spins S1 and S2 will be given by this formula, J is exchange integral. Okay. If J is positive, for example, then the energy will be low when S1 S2 cos theta, right. So, it is a dot product. So, when theta is 0, then this is a positive number. When theta is 0, this will be a positive number. So, if J is positive, energy will be low because it is a negative term. So, if J is positive, S1 and S2 have to be parallel because theta is 0. Okay, so, this is one condition. If J is negative, then the energy is minimum when S1 and S2 are anti-parallel. So, when theta is 180 degree, cos theta will be minus 1. So, S1 S2 will be negative, and if J is also negative, this whole thing will be again positive, then we have a negative. So, energy will be low. Okay. And if J is 0, there is nothing in the system to make the spins parallel or anti-parallel. So, if you take room temperature, at room temperature is 300 Kelvin, let us say. So, there is a kBT thermal energy. Thermal energy is temperature in Kelvin multiplied by Boltzmann constant. So, there is a thermal energy which will make the magnetic moments to flip as a function of time. Okay. So, if there is no energy to keep the two spins parallel or anti-parallel, the neighboring spins will be fluctuating as a function of time. Okay. So, this brings rise to at least 4 different types of material. Okay. So, the first case where the spins are parallel to each other, they are ferromagnetic. The second case, when J is negative, the spins are anti-parallel to each other, they belong to anti-ferromagnetic category. And when there is no, when J is 0, the spins are fluctuating as a function of time. So, they are random in time as well as in space. So, this brings rise to the paramagnetic property. Okay. So, now this slide summarizes how the spins are organized in ferromagnetic material and antiferromagnetic material. So, in the case of ferromagnetic materials, the J exchange integral is positive, and that makes the spins parallel to each other. So, this is the ferromagnetic material. Okay. In the case of antiferromagnetism, the neighboring spins are anti-parallel. This is the lowest energy state. Okay, then there is a special case of antiferromagnetism. So, in this case, let us say I have all chromium atoms, okay, all are chromium. So, this will have 5 Bohr magneton, this has 5 Bohr magneton, and so on. So, all of these tiny atoms have equal magnitude of Bohr magneton. So, you can see that they cancel each other. Okay. So, 5 minus 5, 5 minus 5, and so on. So, the net magnetic moment will be 0, because they are equal in magnitude, opposite in direction. But ferrimagnetic material are a subclass of this one, where the difference is that the neighboring spins have different values of magnetic moment. For example, this atom may have 5 Bohr magneton, this atom may have 2 Bohr magneton. So, 5 2 5 2 5 2 and so on. Okay. So, if you add them together, so 5 minus 2 3, here we have 5 minus 2 3 and so on. So, it will keep adding to a large value. So, when you put lot of atoms together, the neighboring magnetic moments do not cancel as it happens here. So, in the case of antiferromagnetic material, you put even billions of atoms, the neighboring moments are antiparallel, they are equal in magnitude. So, as you keep adding, they will total it will be 0 magnetic moment. However, in the case of ferrimagnetic materials, they are of opposite, I mean they are opposite direction, but they are of different magnitudes. So, the net magnetic moment does not get cancelled. So, it will add up to a very large number. So, here I am using the term magnetization without defining what is magnetization, but I have defined magnetic moment. So, we can use the net magnetic moment is very large for ferrimagnetic material and ferromagnetic materials. So, here again like if these are iron atoms, right. So, 4 Bohr magnetron, 4 Bohr magnetron. So, you keep adding 4 plus 4 plus 4. So, this net magnetic moment will come to a very large value here. Here it is 0, here again it is still a large value. Okay. So, these materials are called ordered magnetic materials because the spins have certain order, either they are parallel or they are anti-parallel. So, these are called ordered magnetic materials. Yeah. Yeah.
So, these ferrimagnetic materials always contain the compound, or the single metal can be ferrimagnetic?
Single material I think cannot have ferrimagnetism because you are talking about one type of atom, right. So, how can one type of atom have two atomic moments? So, it is not possible. So, most often, so for example, you say gadolinium cobalt. So, gadolinium has one type of magnetic moment, cobalt has another type of magnetic moment, they are in opposite direction, because of that they will have some net magnetic moment. So, this can be like gadolinium cobalt, something like that, or there are ferrite, lot of ferrites, there again like two sides there will be different magnetic moments.
This ferrimagnetic we can always see in the compound materials only, not in the single materials.
Compounds or alloys, yeah. There is no single element that has ferrimagnetic property, yes. So, like gadolinium, cobalt, those are alloys, right. You do not have a crystal structure, I mean they are not compounds, you can mix any composition of gadolinium, cobalt. Okay, there are some theories which people predicted, I mean people used to explain why certain magnetic materials have positive J, why some materials have negative J, and this curve is called the Bethe-Slater curve. So, in this case the J is positive or negative depends on the interatomic spacing or radius of the d shell and so on. Okay. These are some of the earlier theories. So, we studied the case of J positive or negative, which leads to ferro, ferri and antiferromagnetic materials. So, J is positive or negative, we have ordered systems. When J is 0, we have paramagnetic materials, because there is nothing to force the neighboring magnetic moments to be parallel or antiparallel. So, in the case of paramagnetic materials, the spins of neighboring atoms are in random direction and they also fluctuate as a function of time. So, if you observe say a set of spins at time t 1, they are like this at time t 1. So, you observe them at time t 2, you can see that they look different because they keep fluctuating as a function of time. And the second point is even the ferromagnetic material or antiferromagnetic material, all the ordered materials will become paramagnetic above certain critical temperature. So, in the case of ferromagnetic materials, when they go above certain temperature called Curie temperature, they will become paramagnetic. So, if you take antiferromagnetic materials, heat them above a certain temperature called Néel temperature, they will become paramagnetic. Okay, so, this is basically a description of different types of materials that we have learnt. So, ferromagnetic material or antiferromagnetic material, the magnetic moments does not fluctuate much as a function of time, whereas you notice that the paramagnetic material had magnetic moments fluctuating as a function of time. Okay, let us do some questions. Sorry. Okay. Are there any questions here? No. Okay, the correct answer is a magnetic dipole. Okay. So, when I say magnetic moment, I am just talking about an arrow which represents a magnetic dipole. Okay. So, I am not talking about anything going around anything. Okay, next one. Okay, majority of you are right. Okay, the magnetic moment of ion atoms come from the uncompensated spin. Okay, it is not just spin. Okay, the spin can be compensated, right. If you have 5 up 5 down, then the net magnetic moment is still 0. Okay. So, in the case of ion atom, I showed you that there are 6 atoms in the D. So, 5 are up, 1 is down. So, we have a net uncompensated spin moment of 4 Bohr magneton. Okay. So, this is the correct answer. Okay, almost all of you are right. In antiferromagnetic materials, the neighboring spins are anti-parallel. Next one. Okay, so in ferrimagnetic materials, there are at least two types of atoms with different magnetic moment values. So, this answer your question. Okay. So, there are at least two types of atoms with different magnetic moments, and they are aligned anti-parallel direction. So, I should have seen equal number of votes for both, okay, because both are correct answers. Okay, now let me play this video. Okay, so I am playing this video to teach you some concept. So, I want to know whether you got it. Okay. So, please type your answer here. What do you see happening there? Okay. I am trying to go through this one, magnetic alignment. Okay, anyway, what you answered is not important for this discussion. Basically, this video I played to bring out the next concept, which is called magnetization. So far I was discussing magnetic moment. So, magnetic moments or the magnetic properties of atoms. So, we were talking about atomic magnetic moments. So, what happens when you put them together? So, they may add up like in ferromagnetic materials. So, I told you that 4 Bohr magneton, 4 they add up, right, to a large value. In ferrimagnetic materials also they add up to a large value, and in the antiferromagnetic materials they cancel out to be 0. So, we have some term to define what happens when you put many atoms together and how they add up. So, it will be a very large number, right. So, instead of having a very large number, so we want that number to be independent of how many atoms you have. Okay. So, we have a term called magnetization. So, magnetization is basically, let us say you take some atom, it has magnetic moment m I, then let us say your material has n number of atoms. So, you add the magnetic moment of all the atoms 1 to n. Okay. So, if you have like billions of iron atoms, so it will be like 4 plus 4 plus 4 plus like that. So, 4 billion, then divide by the volume of the material. Okay. So, we have this definition called magnetization. Okay. So, this is an easy number to understand, and this will be independent of the material's volume or weight. Okay. In this case volume. So, in a material of certain volume V, you have n atoms. So, what you do is like you add the magnetic moment of all the atoms and divide by the volume, then you get a number, and that is what we call magnetization. So, I am quite used to the CGS unit. So, in CGS unit basically we use EMU per cubic centimeter. So, this is the volume. Okay. Then, so this is the volume you see here. Okay. And this EMU is the unit for the magnetic moment in CGS unit. So, this is one definition, magnetic moment per unit volume. Okay. People also do this summation 1 to n m I and divide by the mass of the material. Okay. So, that is expressed in EMU per gram. So, there are some people who study magnetic properties of powders. So, what they do, they measure the magnetic moment of the material, then they measure the mass of the material in gram. So, magnetic moment divided by the weight, that gives EMU per gram. So, some people use EMU per gram, some people use EMU per cc. These are CGS units. I am very familiar with the CGS. So, I am using this, but there are SI units for magnetization. So, when you do this, this becomes a material property. Okay. For example, let us say I have a piece of iron. I do not need to say what is the atomic magnetic moment of iron, but iron will have certain, say 2200 EMU per cc, something like that. Okay. So, when you have a definition like this, magnetization, then you can express the magnetization of many different materials using the units like EMU per cc or EMU per gram. Okay. So, this is the definition for magnetization. Then normally when we measure, we also have another term called saturation magnetization. So, this is the largest magnetization a material can have. That means, when you apply very large magnetic field, all the magnetic moments point into certain direction, then you measure. Okay, that is called saturation magnetization. So, the value I showed here is basically the saturation magnetization of iron, which is around 2200 mu per cc. So far I was telling you that iron has 4 Bohr magneton. Okay. One Bohr magneton is this much mu. Okay. And 1 gram of iron will have so many iron atoms. So, if I take 1 gram of iron and calculate the EMU per gram based on 4 Bohr magneton, okay, I will get a value of 400 EMU per gram. Okay. So, this is based on the fact that each iron atom has 4 Bohr magneton. Okay. However, if you measure experimentally, I give you a piece of iron, you ask you to measure the saturation magnetization of iron, you will measure it to be something like 220 mu per gram. Okay, there is a huge discrepancy. So, so far I have been teaching you that each iron atom has 4 Bohr magneton, and I use this value to calculate the saturation magnetization of iron, then I get some number 400 mu per gram. But I give you a piece of sample iron, you go and measure and you come back with the result of 220 mu per gram. Okay. So, somebody should be wrong, right? Either your measurement is wrong or I am wrong, right. So, there is some discrepancy here. Okay. Anyone has any idea what is the discrepancy? No, not nothing to do with the domain here. Pardon? Temperature, no. Yeah.
This calculation is from the bare atom, so it is
Yeah.
very localized picture.
Yes.
Whereas in a P as a compound, it will have a kindred behavior.
Yes. So far I was talking about just taking simple atoms, but when you have a piece of iron, right. So, you have band structure coming into picture. So, bands form, then you have one spin up band and one spin down band. So, there is a density of states coming into picture. Then based on this picture, you will get this one. Okay. You will get the value of 220. Sorry, I am going in the wrong direction. Okay. So, based on this one, you will have 220 mu per gram. Okay. So, this is the correct picture. So far I was giving you a very simple picture of talking about single atoms of iron, but in reality when you put materials together, there is a band structure, and based on the density of states you see in the material, the difference gives rise to 220 mu per gram. So, this is the accurate picture. The simple picture is for easier understanding, but this is the realistic picture. So, sometimes people ask like whether you can make ferromagnetic materials only based on iron, cobalt or nickel. Most often we do that, we take iron, cobalt or nickel, then dope with something or make compounds out of these materials, and that is how we make ferro or ferrimagnetic materials. But there are many other ferromagnetic materials without iron, cobalt or nickel. So, for example, manganese, aluminum, chromium, platinum 3 and so on, they are also ferro or ferrimagnetic materials. Okay. They have no iron, cobalt, nickel. Okay. So, what determines whether a material will be magnetic or not depends on the band structure. So, you have to come up with this kind of band structures to understand whether a material will be magnetic or not. Okay, so, here I show you some numbers related to iron, cobalt and nickel. So, what is important to see here, you can just notice that these values, for example, iron has a saturation magnetization of 1714 mu per cc, cobalt has 1422, nickel has 484. These are more or less very similar to what we studied before. For example, I told you that this one 4 magneton, 3. You can notice that the trend is similar. So, this is larger, this is medium, this is smaller. Okay. Okay, let us do some questions. Most of you are wrong. Two point two, 1.7 increasing saturation magnetization. So, it should be BCA. Yeah. So, BCA is the correct sequence. So, many of you are wrong. So, I was confused. So, I asked you to arrange in the increasing order, right. By the way, these numbers 2.2, 1 and 1.7, these are the Bohr magnetons of right here. Okay. Because this one I cannot write here. It's okay, no need. Anyway, I don't need to write. Basically, 2.2 Bohr magneton is the magnetic moment per atom of iron in the band structure. Okay. So, in a single atom, iron atom has 4 Bohr magneton, but if you put them together in a material, in a piece of iron, 2.2 Bohr magneton per atom is the magnetic moment of iron. Then nickel is roughly 1 Bohr magneton per atom in a material, in a solid. So, in the case of cobalt solid, cobalt atoms will have 1.7 Bohr magneton per atom. So, these are realistic example. So, iron, nickel and cobalt. So, after a few slides we will take a break. So, I told you that ordered materials will become paramagnetic after certain temperature. So, this is a piece of ferromagnetic materials, and here I am measuring, let us say until this point, this curve is magnetization. So, I am measuring the magnetization of a piece of iron as a function of temperature. So, as the temperature increases, the magnetization decreases to 0 value. Then after this value, I am not measuring magnetization, I am measuring another property. I will teach you this later. So, this property increases with temperature. Okay. So, at this point, magnetization becomes 0, and this temperature is what we call Curie temperature. Okay. So, if you increase temperature beyond Curie temperature, a ferromagnetic material becomes paramagnetic. Okay. So, different materials have different Curie temperature, not important. So, let me play this video. So, here is a paper clip, this is a magnet, this is a string. So, the string has a tension force because the clip is attracted by the magnet. Okay, now, he is heating the clip's temperature increased. So, it is going beyond the Curie temperature, it is not a ferromagnetic material anymore, it becomes a paramagnetic material. So, there is no force of attraction. So, there is no tension in the string. So, the clip just falls down. Let us say the clip is here, clip is cooled down now clip is at room temperature. Now, I bring it next to magnet, what will happen? The clip will be attracted or not? Yes or no? Yeah, it will be attracted. Okay. So, this curve is more or less you can say almost no hysteresis. So, you go this way, I mean some materials will have some hysteresis, but so normally you go up, then you cool down, most likely you are going almost in the same path. Okay. So, ferromagnetic material will become paramagnetic above Curie temperature, but if you cool down, it will be still ferromagnetic. Okay. So, in your school days, you would have learned that if you have a magnet, you do not heat it, because after heating you will lose the magnet. Why is it? Here I am telling you that you heat, it becomes paramagnetic, but if you cool down, it is still ferromagnetic. But in your school days, your teacher or someone would have told you not to heat a magnet. Okay, think about it, we will come to that later. Okay, this is the summary of what we learned so far. So, this is a mind map of what we learned so far. So, I introduced two concepts, that electrons have orbital moment and spin moment. That orbital moment is mostly not coming into picture, only in rarer materials orbital moment has some role, but in materials like iron, cobalt, nickel, spin moment is the one that leads to magnetic properties. So, when there are atoms with unfilled shells, They can lie parallel to each other or anti-parallel to each other, and we will have, when they are parallel to each other, we will have ordered systems. When they have no specific order, we have paramagnetic material. Okay. And when there are atoms with filled shells, they belong to diamagnetic materials. Okay. So, this is a mind map of what happens in the atomic scale that leads to different properties of material. Okay, we will take a short break, then come back to the rest. Maybe we will take 10 minutes. Now it is 57, so we will come back by 12:05.